Okie doke. So welcome everybody who's here. This is the Robert Ferguson Observatory Speaker Series, and this presentation, How Big is Big, is presented by our own Dave Kensiski, who is our one of our RFO docents, a board member, and our previous president. So before we start, I just wanted to remind everybody to please keep yourselves muted to minimize any background noise, and we'll open up for questions after Dave is done presenting. You're welcome to either post questions in the chat, which I will monitor and relay to Dave afterwards, or once he's done presenting, sometimes people jump in and you can unmute yourself then. So either way is fine. So just a little bit for those of you who may not know about the Robert Ferguson Observatory. RFO is run by the Valley of the Moon Observatory Association, excuse me, a 501(c)(3) nonprofit comprised of volunteer, amateur, and professional astronomers. RFO has fulfilled its mission of offering educational programs about science and astronomy for students, the public, and in support of educators for about 25 years now. The observatory is almost all volunteer run and typically serves about 9,000 visitors annually. Obviously, last year was not a typical year, nor is this year, but under normal circumstances. The observatory is located in Sugarloaf State Park and houses a 40-inch reflector telescope, the largest telescope in Northern California that's accessible to the public, a robotic 20-inch research grade or CCD telescope, and an 8-inch 2-meter long refractor telescope. The observatory has a robust volunteer program, and close to about 200 volunteers work tirelessly to deliver programs to the public, offer public star parties and solar viewing events under, again, normal circumstances, provide classes and workshops, and manage all of the myriad of behind-the-scenes tasks that keep the observatory running smoothly. I'm so sorry, I forgot to introduce myself. I'm the volunteer coordinator. My name's Stephanie DeRomelar. So I have to give a little plug for volunteering. It's a great way to get involved in the observatory. And if that is something that interests you, you can feel free to fill out a volunteer application on our website, rfo.org, and I can keep you informed of upcoming new volunteer trainings. The Valley of the Moon Observatory Association, which is responsible for the construction, maintenance, and utilization of the Robert Ferguson Observatory, is part of Team Sugarloaf, which are the 5 nonprofit organizations that formed a partnership to operate Sugarloaf Ridge, including the campground. The other partners include the Sonoma Ecology Center, United Camps Conferences and Retreats, the Valley of the Moon Natural History Association, and the Sonoma County Trails Council.
Well done.
And, and before I hand it off to Dave, we just wanted to also mention we have kept the presentations in our speaker series free to the public to align with our mission of offering educational based astronomy programs to our community, even throughout the pandemic. That being said, if anyone is so inspired to donate to the Robert Ferguson Observatory to ensure that we can continue fulfilling that mission, I will include a link to our donate page on our website in the chat box. And so now I'll hand it over to Dave.
Thank you, Stephanie. Hello, I'm Dave Kensiski. As Stephanie mentioned, I was previously the president. I stepped down from that in order to give myself a little time to do the other things that I love to do with the observatory. I joined RFO. I came up, my father was an amateur astronomer, and so I grew up with the astronomy bug, and then came up with, and then I had children, and kind of all of that went by the wayside. And I came up to the observatory with my son and his Boy Scout troop. I was just a dad enjoying the outing, and I fell in love with the place all over again, and it re-sparked my interest in astronomy. So I put my name on a contact me for more information list, and a month or two later, I got an email saying they're starting docent training. I thought, wait a minute, they're gonna teach me and let me play with all these toys. So I came up, I went through the training, and got involved behind the scenes and started doing far too much, but having a great time doing all of it. And several years later, and here I am. So I think that was back in 2012. So been a few years. Anyway, one of the presentations, one of the things that I do when we're open to the public is host presentations during our star parties. And this is one of the presentations that I do. It's talking about the scale of the universe. And let me see if I test ran all of this so that I should be able to get it all running with just a few clicks. And have the presentation. I'm going to share. Hopefully I'm sharing the right one. And there we go. So I have to remember where to click for this. There we go. So tonight's presentation is how big is big, and to add a second corollary on that, how far is far? As Douglas Adams is keen to say in the Hitchhiker's Guide to the Galaxy, space is big, really, really big. So tonight we're going to go into exactly how, well, not exactly, but to give you a feel for how big that is. But to answer these questions, we need to start with a reference point. When we say it's big, how it's big compared to what, or how far compared to where. So let's start with this this blue globe on which we live. So start with the Earth. It's big enough though that we need to break it, unless you've like hiked from the United States to Singapore, which is a little troublesome to do if you, well, we'll leave that behind. But it's big enough that you really don't have a feel for the scale of it. So let's break it into smaller pieces to understand where we are. We start with the United States, which comprises some 3+ million square miles, and that makes up only 1.6% of the Earth. It's still a big place. I mean, we've all probably flown coast to coast, and it takes many hours to do that. So we can get a feel for how big it is there, but California gives us a little bit better scale. Most of us on the call are probably from California. California is about 164 million square miles, and it makes up 5% of that 3% of the US. Next we zoom into Sonoma County. Wait, can you see that? Here, let me help. Yes, Sonoma County is 1,700 square miles, and it makes up a small fraction of California. And even that is pretty big. You can't think of that in terms of, I mean, you've probably potentially driven that, but if we talk about the park that we're in, Sugarloaf is all of 6 square miles, and you can pretty easily hike that. From one end to the other, you can do that in a few hours. So that gives you a feel for how small this is. That makes up 0.35% of Sonoma County, which works out to be 3 millionths the size of the Earth. So that you take 3 million Sugarloaf Ridge state parks to cover the Earth. So it's a pretty big place to begin with. Well, let's put it into perspective in terms of distance. We've got this convenient line right across the middle of that's on every map. Unfortunately, you can't, when you walk to it, you can't see it. But what if we could build a road and drive along the equator all the way around the world? How far would that be? It's about 25,000 miles along that. So if we could drive that at 65 miles an hour, how long would it take us to get from all the way around the Earth? Never mind the fact that you're crossing oceans and there's storms and the road would be physically impossible to build. If you could drive that at 65 miles an hour, it would take 16 days to drive around the Earth. So that puts things into perspective of speeds at which you're used to driving, probably. But what if you could do it just for fun in the fastest street legal vehicle that's out there, the Bugatti Veyron? Be a little bit quicker. Zoom, see that? Faster. But it would still take you 4 days at the fastest street vehicle that we've got available to us. So the Earth is a big place. Now, what if we could hitch a ride on a ray of light? The speed of light is a lot faster than a Bugatti Veyron. Watch this. Did you catch that? That was fast. Here, we'll do it again. If we could catch a ray of light around the Earth, it would take just over 1/8 of a second. So hold on to that thought, because we'll come back to the speed of light here in a moment. But let's go back to our car now. If our car could go out into space, the first thing it would run into is the moon, aside from the satellites and stuff that Elon Musk is putting into orbit. So if we could drive to the moon, how far would that be? The moon turns out to be about 250,000 miles. Its average distance is 238,000, but that varies. It's an elliptical orbit, so sometimes it's closer to the Earth, sometimes it's farther away. We'll use the 250,000 number because it's an easy number to remember, and it's conveniently about 10 times that 25,000 that it took to go around the Earth. So we can guess that if it took 16 days to get around the Earth, it would take 160 days to drive to the moon. So you got to bring a lot of provisions for that, and there's no convenient place to stop for those brakes, mandatory brakes along the way. All right, so as you can see from this, it doesn't take much to get really big numbers when we're measuring distances to astronomical objects. And so I like to say that numbers in astronomy are astronomical. Sorry. Okay, dad jokes. That's what I do. Okay, so the distance to the sun is roughly 93 million miles, and it would take our friend in the car, of course we have to have the car driving to the sun, 165 years to get to the sun. So that's at your standard speed limit, none of that speeding. This is just another example of how big the numbers can get. Now, if we start throwing around 93 million miles and the distance to the planets, it starts getting some unwieldy numbers, and you run out of digits on your calculator. So what we've done, astronomers have taken the distance to the sun, and we call it 1 astronomical unit, or AU. We are Earth-centric. We don't believe that we're the center of the universe anymore, but we still need to use references that we can easily grasp. So the average distance from the Earth to the sun is 1 AU, and that comes up here in the next couple of slides when we start talking about the distance to the planets. Now, it's not so easy to say how far it is from the sun, or from Earth to Venus, or Earth to Mars, because they're moving around the sun at different speeds. And so the distance varies. Instead of the distance from Earth, we use the sun. We can measure the distance at any given time, but you can't have a fancy chart with distances that keep changing. So instead, we measure the distance from the sun, and so we have all the planets set out here. And this picture, by the way, is scaled to size, but not distance. If this were scaled to distance, it would be really, really big. And if you want to get a feel for how far these distances really are, we have a planet walk in the at Sugarloaf Ridge State Park at the observatory that is a scale model of the solar system. And from the sun to Pluto is about, we recognize that Pluto was once a planet, and we haven't demoted it from our planet walk, but it's about 2.5 miles out to Pluto from the sun, which starts at the observatory. Okay, so let's talk about the distances. 1 AU, the Earth is, as I mentioned earlier, it's 1 AU. It's our measuring stick, 1 astronomical unit. Inside of our orbit is Venus. The next planet in is about 3/4 of the way out to the Earth from the sun. And Mercury is just a little over 1/3 of the distance to the sun. So all of the inner planets, Mars is just a little bit, it's 1.5 times the distance from the Earth to the sun. So at its closest, it's only half that distance. So if it's 93 million miles to Mars, then it's 47 million miles to Mars. To the Earth. It's 47 million at its closest, but at its farthest, if it's over on the other side of the sun, it's the distance from the Earth to the sun and then to Mars. So we're looking at 2.5 times 93 million miles. So it gets pretty far. But even that, the next planet out is Jupiter. It's 5 times the distance. So if we're now looking at some bigger distances, and you'll catch that on the hikes in the park. But things start getting a little crazy from here now. Saturn is almost 10 times that distance out from the sun to the Earth. Uranus is 20, and Neptune is a full 30 astronomical units from the sun. Pretty far out there, which is not surprising why we didn't discover them until we had the latter two of these, until we had some pretty powerful telescopes. So just so we can compare again, back to numbers that we recognize, Mercury is 36 million miles from the sun. We go all the way out to Neptune, and we're looking at 2 billion miles, almost 3 billion miles, 2.8 billion miles to Mercury. That would be some frequent flyer miles if you could fly that one. Okay, so I mentioned this is image size to scale, size to distance, but sorry. Let's put the planets side by side so we can see how they compare up size-wise. In this case, we can see that Mercury and Venus, Earth and Venus are actually pretty close to the same size. The next one in there is Mars, actually, and it's much smaller. It's only about a half the diameter of the Earth, and then Mercury is the smallest. Mercury is 4,800 miles across. The Earth is roughly 8,000 miles across, 7,926. And then Mars, who we hear so much about, is only a little about 6,000 miles across. Going from the Earth, now on the left is the Earth, and we can see that Neptune and Uranus are much larger than the Earth. They're about 4 times the diameter of the Earth. And then we look at Saturn, which is, so remember the Earth's about 8,000 miles across. Uranus and Neptune are around 30,000 miles across. Saturn is up there at 75,000. And if you take the rings into account, it's huge. I don't have that number here, but I seem to remember it's 150,000 miles tip to tip, just from memory. And then Jupiter, our largest planet, is 88,000 miles across. You can stack, if you put Earth side by side across Jupiter, you could put over 10, almost 11 Earths all the way across. And you see that red spot in the middle of it there? That is a storm called the Great Red Spot that's been brewing on Jupiter since Galileo pointed his telescope at Jupiter and saw that it was actually a planet and not a star. That storm has been brewing there for several hundred years, and you can fit between 2 and 3 Earths inside that storm. That's a really big storm. Okay, so this is kind of a picture of the a representation of the 100 largest objects in the solar system. As you can see, we start with the sun, which is huge, and then go to the planets. And very quickly after we get to the planets, we start running into some objects that are really small. Interestingly enough, our moon Ganymede is the largest moon, but our moon is just a little bit smaller than Mercury. So we actually have 2 moons in our solar system, Ganymede, which is orbiting Jupiter, and Titan, which is orbiting Saturn, which are bigger than our smallest official planet. And Pluto should show up in this chart somewhere here. Yeah, there's Pluto on the right. Poor Pluto got demoted. And then you can see we've got tons of teeny tiny little satellites that are orbiting the planets. Okay, so I talked about orbits. As you can see, as this shows, the planets are closer into the sun, have a shorter distance to cover, and so they orbit the sun in a shorter period of time. It only takes about 88 days for Mercury to do 1 orbit around the sun. Venus is getting closer to the Earth. It's almost 2 years for Mars, and then Jupiter. And as we get further out, you can see it takes almost 11 years. And when you get out to Uranus and Neptune, we're talking really long periods of time. Interesting side note, Neptune only in the last several years celebrated its first birthday since we discovered it. So happy belated birthday, Neptune. That was in September of 2011. Now, how fast do these planets spin? So in addition to going around the sun, each planet spins on its axis just like the Earth does. And of course, the Earth's reference is 1 day. Mercury, you'd think it's much smaller. It takes 58 days for it to rotate around its axis. It's actually tidally locked into the sun, which means that its gravity and the sun's gravity keep tugging on it and changing the or to tune the orbit. And so the fun thing to think about is if you spend a day on, you only get, in terms of sunrise and sunset, it takes 58 days for the sun to go from rise to rise again. If you were living on Mercury, you'd only get like 1 or 2 sunsets a year as the sun, or as the Mercury orbits the sun. Venus its day is actually longer than its year, so you don't get it's not very romantic to have, watch the sunrise and sunset. Never mind the crazy sulfuric acid atmosphere that isn't very romantic either. But it takes a long time to get to sunset. And of course, Earth, 1 day, no surprise there. Mars is just a little bit over Earth, just enough over Earth so that the JPL, the folks at JPL who are running the Mars missions that are there, really get their circadian rhythm messed up because they run on the Martian day, and so their start time shifts throughout the year. Jupiter is huge. Remember, Jupiter was 80 something thousand miles across. So you'd think it would take a while for it to do a spin? Heck no. You get a day on Jupiter is just over 10 hours. Jupiter is rotating at the surface of Jupiter. It's rotating at 28,000 miles an hour. In fact, Jupiter is spinning so fast that the Coriolis effect of spinning, like the what's the other term? But the force that you get when you spin something, Jupiter is wider than it is tall. It's expanded it. The spinning rate has expanded it at the equator, so it's further around the equator than it is from pole to pole. Saturn is similarly crazy fast, and Uranus and Neptune follow suit in terms of their spinning really fast. Okay, so you can guess where we're going now when we're talking about the size of our galaxy, of our solar system. It is 5 trillion billion, sorry, 5.5 billion, almost 5.6 billion miles across. And of course, we have to have our car. Driving across the solar system would take almost 10,000 years. At this scale, the Earth is 1,300 times. If this were the scale size of our solar system, the Earth would be 1,300 times smaller than the single pixel that we can represent on this screen. Okay, so let's take a journey out to the stars. This is just a pretty skyscape to show you that how colorful the sky can be out, how colorful the stars are. But it also segues nice into the Hertzsprung-Russell diagram, the HR diagram. This is a very common tool that astronomers use to to differentiate the types of stars and the sizes they get. We could spend an entire presentation on this. Most of you would probably fall asleep, but there's so much detail in this. I'll go through it really quickly. Basically, from the lower right up to the upper left is what we call the main sequence. As stars progress along that, the ones to the farther to the right and lower down are smaller. The ones to the farther to the left and higher up are hotter, smaller and cooler, sorry, on the lower right, to hotter and brighter and larger to the upper left. And then we have these this segment that goes off to the side in the upper right, which are where our giants and supergiants are. And then other types of stars, white dwarfs and neutron stars, show up in the lower quadrant there. So this you can see we've pointed out where Sirius and some of the supergiants that you see names of Betelgeuse and Betelgeuse and Altair and Antares and so forth. And for Star Trek fans, Wolf 389 down there in the lower right-hand corner, that's where the Borg Wars took place. So Star Trek, the Next Generation. Classic Trek, didn't know about that. Okay, so now let's start talking about the stars. You remember this slide where we talked about the sizes of Earth compared to the larger of our planets. Now let's take Jupiter, which remember is 11 Earths across, and compare that to stars. Wolf 359, our Borg Wars, is actually the red giant. The red dwarfs aren't that much bigger than Jupiter, so you can see it's only slightly larger. And then our sun fits in there as somewhat larger than both of those. And Sirius is the brightest star in our sky. It's not too much. It's about twice the size of our sun. It's so bright because it's not that far away. I think it's 10 light years. I should have that number ready for this, but it's relatively near. And so because of that, while it is brighter than our sun intrinsically, if you're the same distance away, it's super bright in our sky simply because it's brighter than our sun and it's near. But as we go further out, now Sirius is on the left side here, and we've got Pollux, one of the twins of Castor and Pollux in Gemini, is markedly larger than Sirius. And then Arcturus and Aldebaran, these are the red giants. Arcturus in Boötes, and Aldebaran is in Taurus, the bulls, the big red star in the bulls, in the constellation of the bull that represents his eye. And then if we take Aldebaran and move it over to the left, Rigel, in the big bright star, one of the brighter stars in Orion, to Antares in Scorpius, and Betelgeuse also in Orion. You can see how big things are getting. Betelgeuse is even larger now, but even this is a red supergiant now. And Betelgeuse, interestingly enough, is one of the stars which it made news recently because it's dimming, and you probably heard that some people were saying that it might supernova at any time. That's true. The dimming had nothing to do with that. That had to do with dust and material that's orbiting it. But Betelgeuse is a star that is ready to supernova, and at the end of a star's life, as a star reaches the end of a larger star reaches the end of its life, it'll grow up it'll keep expanding and actually get larger into this red supergiant stage. And then when it runs out of fuel and can no longer keep its gas expanding, it collapses down in an instant. Most things in the universe, in astronomy, take millions or even billions of years to happen. But when it runs out of fuel, it collapses in an instant, and it makes one of the most powerful explosions in the universe and sheds its material out to create new stars. So Betelgeuse is ready to do that any day now. And when I say any day now, I say it in astronomical terms. It could actually happen today, or it could happen in 5 million years. But from an astronomical term, that's any day. So it's worth keeping your eye on it, but don't hold your breath unless you've got really good breath control. Okay, so Betelgeuse is a pretty big star, but even that pales when we start looking at things, other of these supergiants that we found, Mu Cephei, VV Cephei A, VY Canis Majoris. You get to this point, and we've run out of names. First of all, the stars are far enough away that they're too dim for us to see with the naked eye, or they're dim enough that they're not prominently named stars. So they get funky catalog name numbers, which represent the when they were discovered or when they were cataloged with respect to the constellations they're in. So you can see this, if Betelgeuse was big, we've got VY Canis Majoris, but even that pales when we start looking at this NML Cygni and UY Scuti. UY Scuti has got to be one of the coolest names that I've come across. UY Scuti, it just rolls off nicely. Well, anyway, for me. And at the time of this, there's actually, I believe we've discovered another one that's larger, but not by any order of magnitudes. I didn't get the name of that to update this slide. But if we were to take UY Scuti and compare it to our solar system, now our sun is 870,000 miles in diameter. But it's actually too small to see at this scale. You can see the little representation on the left there. UY Scuti is 1.5 billion miles. So from 87,000 to 1.5 billion miles in diameter, you could fit 1.3 million Earths inside our sun and 6.6 quadrillion inside of UY Scuti. So this is one big star. All righty. Whoops, wrong direction, sorry. Now, let's put UY Scuti in the center of our solar system where the sun is. And dun, 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 dun. We don't have animation audio effects, so I have to add them. It would consume most of our solar system and look something like this. That's a big star. Okay, so remember I mentioned that we'd come back to the speed of light. In the solar system, we took the distance from the Earth to the sun as our yardstick and called that 1 AU. And even that's too small when we start talking about distances to the stars. And so we've come up with the term called light year, which is the speed of light taken, how far light travels in a year. So it goes at 186,000 miles per second. You can see all the math, 1 light second, it's 186,000 miles. And then you multiply that by 60 to get minutes, multiply another 60 to get hours, multiply 24 to get days, and then 365 to get 5.8. That's 100,000 million billion trillion miles, almost 6 trillion miles for 1 light year. So when you hear the term 1 light year, it's easy enough to just round it, think 6 trillion miles. And naturally, we have to have our car to go that distance, 6 trillion miles at freeway speeds. It would take you 10 million years. Our nearest neighboring star is Proxima Centauri, and that's represented by the little circle there in the middle, or that arrow points to. It is 4.22 light years away, so rounded in round numbers, it's 24.8 trillion miles to our nearest neighboring star. We won't bother with the car. We can do the math and figure that out. But as we go out into the solar system, or into the galaxy, we run into globular clusters. This one happens to be Omega Centauri, which unfortunately fortunately is a really cool naked eye cluster that you can see. Unfortunately, you have to be south of the equator to see it. It's a southern hemisphere object, but it's 150 light years across. So remember, it's 4 light years to our nearest star. This object in our galaxy is 150 light years across. It's about 18,000 light years away, but at that distance, it's still naked eye visible. This has hundreds of thousands to millions of stars gravitationally bound and orbiting the center of mass of this thing. And actually, of late, they believe that there are black holes at the center of globular clusters, kind of shepherding all of the objects in there. And these clusters are so densely packed with stars that if you could survive on a planet orbiting one of these stars at night when your sun has set, you would have enough light from your starlight from the neighboring stars in the sky to read a book by quite easily. Super, super densely packed. So we move out further into the scale of things, and we run into our Milky Way galaxy. If you remember, we were 150,000 light years across, 150 light years across the globular cluster. Our Milky Way is 120,000 light years across, give or take. The numbers keep getting tuned one way or the other. And we live in a spiral arm about 2/3 of the way away from the center of the galaxy, which is a good thing because there's a supermassive black hole or two in the center of our galaxy, and they give off enough radiation that if we lived too close to it, we would not have been able to, we would not be able to survive. We would not have evolved. Okay, so our Milky Way is actually a spiral galaxy. If you were able to get out and look back on it, which of course we can't, this is not a photograph of the Milky Way galaxy because we'd have to be 300,000 light years away to take this photo. This happens to be a photo of our neighboring galaxy, the Andromeda Galaxy, and it is 2.5 million light years. So remember, our galaxy was 120,000 light years across. This is now 2.5 million light years away. And oops, there you go, 2,500,000. Not as good at hitting the button as I am at talking, am I? Excuse me a second. This actually can be seen naked eye, and it is the furthest object that away that you can see naked eye without the aid of a telescope. On a really dark night, we can point this out at RFO when it's up. This time of year, it doesn't rise till later at night. But so every star we see, everything we look at when we look in the sky is part of our Milky Way galaxy. It's in the 120,000 light years away range. In fact, most of the objects we see are tens to hundreds to thousands of light years away. A couple of them are tens of thousands, in the tens of thousands. So when you start thinking about this, you're looking.
Do you want to watch news?
Yeah.
Excuse me.
No,
You're
that's
looking at
okay.
2.5
on
million.
TV.
light
You want to
years.
watch it on?
No, that's all right. I don't.
Okay, so our galaxy, the Milky Way and Andromeda, are two galaxies in our local galaxy cluster. So as we move out now, you can see the 1 million light years reference on this chart. So our galaxy cluster consists of the galaxies that are locally gravitationally bound. All of these galaxies are orbiting around each other. In fact, the Milky Way and Andromeda are on a collision course to collide with each other in some 3 or 4 billion years. So you don't have to worry about it yet. And in fact, the good news is when two galaxies, because galaxies are so much empty space, when two galaxies collide, there are very few, if any, collisions of stars. They all get twisted around and moved out of their orbits. The planets usually follow the stars, but the stars get twisted and moved out of their orbits, and some of them get thrust out into galactic space, and some of them, but the two galaxies will go through a cosmic ballet and ultimately become one over the course of a few million years in that transition. So that's our galaxy. If this galaxy, IC 1101, astronomers can get pretty boring in their naming conventions, but IC just happens to be the catalog, and 1101 is the catalog number. This galaxy itself is the largest galaxy that we have discovered, and it's by itself is 6 million light years across. It's over 1 billion light years away. It's in the constellation Virgo, but it has a diameter of 6 million light years and the mass of 100 trillion stars. If we were to put that on our local group, it would consume both Andromeda and our galaxy and pretty much all of our local galaxy cluster. That's a really big galaxy, almost as large as our entire local group. Okay, as we zoom out from our local group, we run into superclusters. So galaxies are clustered together like our galaxy cluster, our local group. And our local group now is just the one dot in the middle of this slide. You can see the 10 million light years out. So we've now zoomed out about 10 times from that previous one. And we've got all these other clusters of galaxies. So galaxies cluster together by gravity, and then the clusters are grouped together into these superclusters. And in fact, if we zoom out even further, now we're out to about 110 times further, the superclusters cluster as well. And you can see Virgo supercluster right there in the center. That's the supercluster that our local cluster is a member of. And if you zoom out even further, you reach the edge of the observable universe. And the light from this has been traveling this represents the farthest away that we can see in the universe. And this distance is 93 billion light years. The light from the universe is expanding, so that the light from these objects that are this far, that are at the edge of this, have been traveling for 13 billion years to get to us. So what is 93 billion light years? In miles? That's a lot of miles. 546 sextillion, 700 quintillion, 482 quadrillion, 330 trillion, 9 miles. That's a big number. And naturally, we have to take our car. It would take our car 960 quadrillion car years to get across the observable universe. Okay, so let's kind of recap. We started looking at the Earth, which we thought was pretty big. At least I tried to convince you it's pretty big, but we kept building up to our solar system, which is much larger than our Earth, and then our local cluster, our local stellar neighborhood. We talked about some of the stars, then the Milky Way galaxy, our local group of gravitationally bound galaxies, the clusters, the supercluster that we're in, the supercluster clusters out to the edge of the observable universe. So are we done? Well, as far as what we know, yes, but there are theories that our universe is just one of a multiverse. And if galaxies can cluster into galaxy clusters, can multiverses cluster into multiverses clusters? And the only thing I have to say to that is the end. And thank you. Questions? Comments? Berating the speaker?
That was great, Dave.
Yeah, thanks so much. That's awesome.
Thank you. Thank you. It's a little weird to do it and not have feedback. You know, I can't tell if my dad jokes are like falling flat on the ground because you're all
I'm
muted.
clapping. Michael is raising his hand. Michael, feel free to unmute yourself if you'd like to ask a question.
Hey, Dave, this is Michael.
Hey, Michael.
Dave, thanks for stepping up. I really enjoyed that, and I look forward to learning how to present that to other people. Thank you for doing that tonight.
Absolutely. You're most welcome. I had fun doing it. Am I really that? This lighting is messing up my.
Yeah, you're a little fuzzy.
Am I looking kind of ghostly?
Yes.
Yes, you look very alien.
Ooh.
It's a cool look.
I think it's an improvement. I think it's an improvement, Dave.
Thanks, Rich.
Character from Star Trek.
Yeah, I'm beaming in. Let me see if I can unblur my background.
Dave, what is the name again of the closest star to us out other than the sun?
Proxima Centauri.
What was the first one?
Proxima Centauri.
Proxima.
It's part of the Alpha Centauri star system. Background and filters. If I go to none, oh, I see. It's because the sun's right there. How about if I do this?
Exactly. Hey, Dave, I have a question.
There we go. Okay.
So you made this presentation, and I've seen it before, and this is one of those wonderful things where Rob has offered this to us, right?
Yes,
I mean,
Rob actually. Go ahead, sorry.
When we do public nights, he's been really gracious to offer to many people to do this. And so how did you get permission from him to allow you to present his presentation?
I emailed him and said, hey, Rob, we're talking about doing a presentation for the speaker series. And I've been asked to do a presentation and I'd like to use your material, but I'll give you first right of refusal if you want to do it. And he said, oh, no, you go right ahead.
Yeah, exactly. And, you know, one of the things I noticed, I know Elaine is doing a lot of work on this, but I noticed Jack has all of his night sky stuff on the lecture, the classroom computer. So I just want to make maybe make a connection with you and Elaine that I would like to study those. And I would like to, you know, I'm up there sometimes and I like to fire up the TV and the computer and use those, but I want to make sure that I am not, I want to make sure that I'm respecting intellectual property. Can you help me with that over the long term?
Yeah, we can talk to Jack about working that in. There's no problem, certainly, with you reviewing the material and learning it, and then we can coordinate with Jack in terms of presenting. I believe if he prepared it using RFO material, it's technically RFO copyright, but there's no reason to step on toes. We can talk to Jack.
But sometimes I'm up there and I'm just studying and reading, and I want to make sure that I don't mess anything up and just that I can look at that stuff. I've taken those classes. Certainly. And I have his handouts, but what's on there is even more. And sometimes I just sit and go through it myself. So maybe on another day that you and I can touch base on that.
Yeah. And thanks for the segue. I'll do a shameless plug that Jack has talked about offering the classes again once we are after COVID and after COVID restrictions are released. Though he'll do it by series, so there won't be a summer series because it would have to start like now. But the fall series it's looking likely that we'll be offering that again up at the observatory. So that's kind of exciting.
Dave, I had a sort of a question or kind of confirming that this is correct. So I was at the observatory once and we were talking about the planet walk. Actually, maybe you're the one who told me this, I'm not sure. But somebody said, based on where the sun symbol is for the planet walk, which is right there, very close to the observatory, they said if you walked to, if we took that same scale as the planet walk, then the closest Proxima Centauri, if I'm saying that correctly, would be in South Africa.
That is correct.
That is.
I did that math.
Oh, you did. Are you the one who told me that?
It might. Well, I shared the number. I shared that. So probably, but yes, I did the math to figure out where it would be. And I'm pleased to find out that it does fit on the Earth. But if you want to extend the walk to Pluto and go all the way to Proxima Centauri, you've got to walk to South Africa. I
thought that was an amazing. It just stuck in my head.
Yeah. The other fun one is a couple of years ago, they were talking about a possible ninth planet that is outside the orbit of Neptune, and not Pluto because they demoted, but there's supposed to be another giant planet that's potentially another giant planet that's orbiting out there. And if you hike to Pluto a little bit further on, if you go up to the top of Brushy Peak, which is like a quarter of a mile past Pluto, you can see over into the Napa Valley. Mm-hmm. And that orbit is very elliptical. I did the math for this one too. And the closest it could get is the next range over on the other side of Napa. That's the closest it could get on the scale. And at the farthest, if you look off to the right from there, you can see Mount Diablo. And that's about how far how elliptical the orbit is.
That's amazing. I
just like putting things into scales that you can visualize or try to count on fingers. When I run out of 10,
No, exactly. It's yeah, it helps wrap your head around it a little bit.
Yeah.
Along those lines, what is the scale of the planet walk?
I don't remember the actual number. We do have it published somewhere, probably on the handouts. I do know that if you're walking at your normal pace, you're going faster than the speed of light. So be careful how much you do that, because that you start messing with the space-time continuum, and you end up with everybody being really old when you get back. No, just
I know I should have that information. I don't have that in my head, but maybe that's on our website. I'd have to look at that.
I think it's on the flyer, but
any other questions for Dave? You can, like I said, feel free to unmute yourself.
And also for you, Stephanie, and the others that are organizing the speaker series. Dave, again, thank you very much for being here tonight. And Stephanie and others that are organizing the speaker series, thank you. It seems like we have some great people set up, and it's really easy to do it. So thank you for everything that you've done, the speakers that you've put in place, and the other tools so that we can simply come and enjoy these things. Thank you.
Great. You're welcome.
Yeah.
Thanks very much, Dave.
Absolutely, you're very welcome.
Well,
maybe this is a good segue to introduce our June speaker, and that will be John Bunnell, who is an engineer at the Space Sciences Lab at UC Berkeley, and he designs, tests, builds equipment destined for space, and he'll be talking about the NASA Greece sounding rocket program. So we're looking forward to that one as well.
Very cool.
Hope everybody considers joining in.
Yeah, we'll have those. You can register again on rfo.simpletix.com. I think it may be up on there yet, but it may not be active yet. So anyway, check back soon. And
I think it is. I
that
think
one.
it's live right now.
oh, is it? Okay,
I think.
I'll confirm.
If not, it will be soon.
Yes.
Well,
Great.
way to
Well,
go,
thank you
Dave.
all.
Appreciate
Thank
it.
you
I have a question for Dave, if I can. It's a little bit off of the topic.
Sure.
But hey, Dave, I know that you do a lot of hiking and you've been really active with the Boy Scouts. Since we're online real quick, just briefly, I'm looking to continue to participate with the Planet Walk and organize hikes on a somewhat regular basis. So I'll just kind of throw that out there to you, Dave, and others, if you all can help me to organize with John Roney to have maybe almost a monthly Planet Walk hike.
That'd
So
be
I'll
fun.
just kind of throw that out there. That's a really simple thing to do. It's not very far to go. And I think that's a wonderful, especially in the era of COVID, a simple socially distanced way to do it. And Leo does such a great job getting us text out there. I think that's a wonderful way because people are constantly walking by there. So I'll just throw that out there that I'm available to lead those hikes. And Dave, you and I have done that before, right?
That was a lot of fun. Yeah.
Yeah, and it's super simple. And what a great way. Speaking about, that's my trying to get involved in public outreach and things like that. Super simple. You just show up and then go for a walk with people.
I can start working on getting rid of my COVID-20.
Okay, well, there you go. It's a plan.